Today we will be learning about systems with accelerations or shaking. Let's start with a static body cylindrical tank. And I'm going to make this look like a cup or glass. So let's make it a little smaller. We're going to recenter the Y-plane. We don't need any baffles. And we can change the bottom settings as well. So now it kind of looks like a glass or cup, like you would see in your kitchen. Let's add some free surface dynamics. And I'm going to drop the liquid down a little bit. Now we're going to look at external accelerations. Right now it just has gravity as an acceleration, but we can add additional motions or movements that will influence the velocities and accelerations of the fluids. In this drop-down menu, we can choose different types of external accelerations. I'm going to start with linear shake. We can define a shake direction in the X, Y, or Z plane. I'm going to leave it at X. We can decide an amplitude measured in meters. And let's do 60 revolutions per minute. So 1 per second. There's also some simulation parameters we should adjust. 3 seconds is enough time for our simulation. And the output frequency, let's set it to a lower interval since the simulation won't be running for very long. In the output panel, we can also adjust the fluid settings now, and we want some surface velocity and an energy dissipation rate. With these options activated, the solver will automatically print the fluid velocity and energy dissipation rate along the surface, as well as the associated mean, minimum, and maximum values. We are now ready to run the simulation, but there's a couple things you should keep in mind. Since there are no moving bodies or inlets available to define a reference velocity, the solver is using the default reference velocity of 1 meters per second. Depending on the nature of the external acceleration, the actual fluid velocity realized in the system may exceed this reference value. In such cases, the time steps should be reduced to generate acceptable LB densities. There's also some important parameters that you need to be aware of. For example, surface tension would be an important variable to consider in a small geometry like this one. Larger systems would be more influenced by variables like inertia or viscosity. But in a smaller system like this one, surface tension is going to play a much larger role. And one more setting that is going to be very important for these kind of simulations is the contact angle. That will decide if your solid surface is hydrophobic or hydrophilic. Here we will use the default contact angle of 130 degrees, which corresponds to a somewhat non-wetting hydrophobic glass surface. Let's go ahead and run our simulation with the linear shaking. I'm going to quickly refresh the data, and let's start taking a look. If you remember, we assigned this model to have a linear shaking back and forth, and we can see the fluid moving the way we would expect if we had a cup and we're just sliding it back and forth. If we wanted to see the cup itself moving relative to a lab frame, we can turn on the lab frame. So let's go ahead and select that and press play again. Now we see the cup sliding backwards and forwards with the linear shaking motion we described when we set up the model. Let's change some colors so we can see it a bit better. So let's change the color of the free surface. Let's use these colors to indicate the positions. And now when we press play, we can see that the color is indicating how high the liquid is moving. Let's look at velocity, which of course can be very interesting. And let's look at the z-slice of the model so we can look at it from the side. And we can turn off the lab frame and reduce the maximum value so that we can see the motion a little easier. Note there are two options available for defining velocity. The relative velocity, shown here, is the velocity of the fluid relative to the moving wall. The absolute velocity, which is an additional coloring option, is velocity relative to a laboratory fixed observer. We can isolate a specific component of the velocity vector, so we could just look at the velocities in the x direction, for example. That was linear shaking. Let's see what other options we have. Let's try orbital acceleration. That's simple to do. We can just go to the main lattice and change the external acceleration drop down to orbital shake. Since orbital motion happens in two planes, we need to define what that is. Let's use the plane defined by the x and z axis. We enter an amplitude. Let's use 3 centimeters. And let's use 120 revolutions per minute. This will make it go a little faster so we can see what that looks like. So let's go ahead and run the simulation. We will now see some circular motion with the fluid in the model. Let's refresh our data and turn on the lab frame and press play. Let's color the free surface according to the Y position. So this will show how high the fluid is going, and we can see it rotating. Let's refresh the data and press play again. And you can see the surface tension coming into play with the fluid sticking on the side. And we'll refresh again. And let's watch it just for a little bit longer. I think it looks kind of cool. Let's go ahead and look at another motion type. Now let's look at rocking. We need to decide an angle to show how much we want the model to rock. So let's use 30 degrees and 90 RPM. The axis mount point is something you need to keep track of. The rotation axis mount point defines the root of the rocking axis. Here we have, by default, a rotation axis pointing in the x direction with the axis root located at 0, 0, 0. In this system, we want the rocking axis to extend through the bottom of the vessel. Since the dish bottom head has a thickness of 0.015 meters, we will drop the rotation head to that location. Here is our model. Let's refresh the data, turn on the lab frame, and press play. And it looks like the motion is consistent with the axis and rocker angle specified in the preprocessor. This kind of data is kind of fun to watch, if you ask me. Like I mentioned before, the time step is something you will want to pay attention to and adjust for your model. We used really simple models and the default setting worked really well. So for example, the solver doesn't have something like a tip speed or reliably defined reference velocities, so you still need to pay attention and define those time steps manually. Lastly, I already mentioned the need to turn on surface tensions for a small model like this one, as well as the contact angle. I've shown you two examples of fairly straightforward and simple models just to show you the basics of adding accelerations. But now I'm going to show you a more kind of advanced model that requires a little more customization. Let's look at an example where we want the model to move in this figure 8 motion that I've defined here. I'm going to use the same cup model that I did before, but instead of rocking or linear, I'm going to choose a custom translation. Now I showed you the figure 8 motion that I want and the equations to describe that motion. Let's bring that information into the code now. Along with importing the lateral motion of the figure 8, we also will need to define the initial velocity of the motion. I called those two variables A and B before, and I'm going to use those same letters and create global variables. I'm going to rename these two variables as A and B. We need to initialize these variables and put an initial value in. Let's give A a starting point of 0.2 and B, let's make it a little faster. We'll make it 4. Back to our main lattice. And let's edit the acceleration. We have our equation from before. And we need the acceleration here. Let's start by defining the x component of the rigid body acceleration. So the equation is minus a times b squared times the sine of b times t. Let's define the z component of the rigid body acceleration. Since we're defining the acceleration, one more thing we need to do is reconstruct the position from the acceleration. So the code needs to integrate this motion. And so the code needs to define the correct parameters. For example, initial position and initial velocity. The initial position isn't that hard. We just put 0, 0, 0. But the initial velocity, you need to specify. Here again are the expressions for the velocity. At time 0, the initial velocity in the x and z directions are both equal to 0.8 meters per second. We're going to turn on the lab frame, refresh our data, and press play. Notice that the liquid has a little bit of initial velocity, and the model has motion at time 0, which means that the fluid will have a non-zero acceleration at time 0. Let's add some colors and put it on the y coordinates. Let's watch it run now. Okay, let's export a movie and see this operate in real time. You can see that the motion is this figure 8 that we defined with the equations. So this is really good for modeling things like shaker flasks, or even things like culture bags, things that you might shake linearly. So there's a lot of applications for adding accelerations to these models. Thank you for watching this video about accelerations in M-star CFD. If you have any questions, don't hesitate to reach out.